Welcome back to the fifth video about the details of the A1335 Precision Hall Effect Angle Sensor. In the previous video, we learned and extended our library accordingly how to write the extended addresses of that thing. And we used that to actually set the output rate. That means we can now influence how many samples of the angle that thing is averaging until it gives out a new angle reading. Card here, link in the description. Today, we want to find out how that setting is actually influencing the noise level. And by the way, it's 33 degrees currently here in my lair. Enjoy! Just a short recap of the output rate setting. So you have 8 settings available, so really just a 3-bit value. And setting 000 means each time one sample from the analog to digital converter is taken, and you get an update period of 31.25 microseconds, and that corresponds to an update frequency or output rate of really 32 kilohertz. So this is the rate the analog to digital converter really delivers data, an angle from all the Hall elements. And then you can increase the samples that are taken by 2 to the power of our value here. So that goes up until 111, so 2 to the power of 7, 128 samples. And then of course your update period is 120 times as long, so 4 milliseconds, and your update frequency is only a 128th of the 32 kilohertz here, so 250 hertz. Please note, this is not a moving average. So each time the chip generates a new angle output that you can read from its registers, it starts anew by summing up n samples it gets from the analog to digital converter, and then at the end it simply divides that by n. I also changed the sketch a wee bit for our noise measurements. No real functional changes. So in the setup, I removed all that micros timing stuff here for our function and removed all serial prints. But for real library errors that might occur or not, hopefully not. And in the loop, I have now only a delay of 25 milliseconds, so we read a lot of data and see how the noise is really doing. And I also only read the angle from my left chip, and that's the only value I print out on the serial port for the serial plotter. I multiply that by 100 because, so we see on the serial plotter 100th of a degree, because that, you will see it. It makes the bit noise or any noise very visible because it scales up very nice in the serial plotter. Okay, let's have a look at the noise then. Remember, that's only one sample, so basically no averaging. That's directly the digital noise we get from the digital to analog converter. And I say that's about 4 least significant bits. Maybe here's a peak and there's a peak in between. So generally 4 least significant bits, and maybe, if we count these 1 bit here up and down, maybe 6 on the extremes. I've changed the settings now here for the output rate to 16 kilohertz, so 2 samples. And as you can see, the spikes, the plus minus 3 LSB spikes, are practically gone. Well, you can watch it for a while if it occurs again, but I don't think so. We're down to a frequency of 8 kilohertz now, so 4 samples averaging. And as you can see, now even our plus minus 2 least significant bit spikes here become, less frequent. Let's call it that, less frequent. We're down at 4 kilohertz, so averaging over 8 samples now. And as you can see, our plus minus 2 least significant bit spikes are really just far and few in between. I'm almost willing to call that a noise of 3 LSB. Yeah, let me take a hard copy and watch it a little bit longer. Down to 2 kilohertz, that would be averaging over 16 samples. So I've been staring here at the serial plotter for a while now, and these plus minus 2 LSB spikes, they're gone completely. We're down to 2 LSBs noise. Averaging now over 32 samples, we're down with our output rate to 1 kilohertz. And we're still at 2 least significant bits of noise, but you see these minus 1 least significant bit spikes, they get fewer and fewer, and this would be actually only 1 LSB noise, but that would be unfair because we just saw that we have still sometimes 2 LSB noise. So I will wait until that occurs again and take a hard copy. Here they are. Let me take a hard copy real quick. Output rate down to 500 Hertz. So we are averaging now over 64 samples. And it looks like 0 LSB noise, but that's not possible. So stay with me. There's some noise. And I also saw minus 1 LSB in between. So I will watch this a while and maybe we can see again 2 LSB noise. It was there, believe me, just before I started recording. Now we're back at 0. Or just let's call that 1 LSB. I mean, maybe I was hallucinating. I don't know. And finally, the maximum averaging over 128 samples that we can do here. Output rate is now down to 250 Hertz. So, we're staring together here at a flat line. The only indication that something is happening is that our sample counter here, or the x-axis of our serial plotter, is counting upwards down here. That's it. 0 LSB noise. To summarize, when we were not averaging our analog to digital converter output, so each sample is directly delivered at a rate of 32 kilohertz, we had a noise of about 6 LSB peak to peak. To put these 6 least significant bits into relation, that's somewhere about 0.48 to 0.54 degrees of our full 360 degrees. So let's say aboutish half a degree noise. As soon as we just averaged over 2 samples, of course halving the output rate to 16 kilohertz, the noise went down to 4 LSB. That's between 0.32 and 0.36 degrees. So let's say a third of a degree. And with 4 samples, again, output rate down to 8 kilohertz, we still have, 4 LSB noise here. Maybe subjectively a little bit less, but the next step came with 8 samples averaging down to 4 kilohertz output rate. Then we're down to 3 least significant bits, and that's about 0.24 to 0.27, so let's say a quarter degree. And that trend of course continued, 16 samples, 2 kilohertz output rate, 2 LSB. We are now down to an error of noise of 0.16, 0.18 degrees. So a fifth of a degree, generously. And at 32 samples, we are still at 2 LSBs, but you can see, the noise density is significantly reduced. At 64 samples, we're down to 1 LSB. Far and few in between, spikes, but still 1 LSB noise. And 1 least significant bit is somewhere between 0.08 and 0.09 degrees. So less than a tenth of a degree noise. And finally, at 128 samples averaging and output rate, of course, down to a meager 250 hertz, we had a flat line. No noise observable at all. And that's, for a change, a magnetic sensor I really like. That's how the output signal has to look like, at least in my book. So that was angle averaging via setting the O-rate parameter on the extended address. However, that's only the very first signal processing step that we can actually program in the A1335. There is a lot more going on here. There's a reason that thing has a built-in 32-bit CPU, and I just want to give you an overview what you can expect during the next few videos. So here at the top we have the analog front end. We also saw that in the block diagram I showed you in the basics video, card here, link in the description. That is followed by some hardwired digital signal conditioning, and then the real angle computation from all the measurements taken of these many arranged in a circle Hall elements. And then we were here at P1 angle averaging, which we can program using the O-rate parameter, so the output rate. Next, after we average our angles, we can apply an infinite impulse response filter of the second order. That's programmable via 3 numerator registers and 2 denumerator registers. You can set a fixed exponent for all numerators. And also you have here a flag for switching that on and off, and a filled error parameter that you can basically use to reset the filter if the output of the filter gets too far apart from the real input. If you are interested in that infinite impulse response filter stuff, let me know, because that doesn't have a real priority for me now. That's not used really to improve the signal quality here, but that's used to basically implement a low-pass filter to filter out mechanical noise you might get here into the system. Remember, this is automotive chip, so things are vibrating, including our sensor and our magnet on whatever axis it's attached to. And you might want to filter out using a low pass these vibrations from your data. And I will skipping here over that angle compensation like all the other red mark boxes. Some remarks about them at the end. Anyway, then you have optional a pre-linearization rotation. That's just a flag that tells you if the chip should measure the magnetic field clockwise or counterclockwise. Then, if we are using linearization, more about that in a second, we have here an optional pre-linearization offset. Interestingly, in the data sheet, that's called the lin_offset, while in the programming guide, that's called the sec_lin offset. Yeah, things are not really consistent between the data sheet and the programming guide. But anyway, that's just subtracting or adding an angle to our value so far to set a 0 point that we like. And then comes the either segmented linearization or harmonic linearization. I talked several times about that, but if your magnet is off axis, we get not a linear reading, but we get a sinusoidal error on our angle reading. And there are two methods available here in the chip to compensate for that, and either segmented linearization or harmonic linearization. I think you can even apply both. But anyway, that's quite a complex thing. And that's programmed via the SRAM registers 0C to 1A, plus 4 more flags you can set elsewhere. So a quite complex linearization algorithm we have there. And then after linearization, we have again optional post-linearization 0 offset. That is, if we want, we can apply another angle offset to our result. And that's followed by another optional post-linearization rotation. That is, we can switch again from counterclockwise to clockwise and vice versa. Finally, that's fixed. The angle is rounded to 12 bits. So up to far, I think we're calculating with a 16-bit value. That's 12-bit value is what you actually get in the primary serial interface and the primary register. And finally, we have another flag where we can add 180-degree rotation to the whole output. That's useful if you have actually a A1335 version with two independent, automotive for redundancy, dies in it. And these dies are rotated to each other 180, I can't really show that with my fingers, 180 degrees. And setting that flag, you can compensate for that. Finally, the A1335 can also be used for so-called short stroke applications. Meaning we're not really measuring an angle from 0 to 360, but maybe just something plus minus 5 degrees. Okay, short stroke. Or minus 2 degrees. And the whole short stroke processing stuff here allows you to blow up that little scale from plus minus 2 degrees again to plus minus, the whole 12-bit value. Anyways, there are also some checks and limits you can set for that short stroke. But I'm personally not really interested in this short stroke stuff, so I probably won't talk about it. Sorry. That's it for today. Temperature is down. We are now, almost after sundown to 32 degrees Celsius. There's a little bit of wind here going through the den, so it's a bit, got a wee bit better, but I have the feeling though humidity has gone up, so yeah, not really an improvement. But anyways, next time we will start to tackle, because I'm very interested in that, the linearization stuff, and we'll probably start off with the two pre-linearization options. That is to set an 0 offset to tell the chip what we want to be 0 degrees, and to tell the chip if it should increase the angle going clockwise or counterclockwise. Because remember, we have a left chip and a right chip, and they are mirrored. And yeah, maybe I want the angles on both to be counted in the same direction, looking from here. Anyway, till next time, bye.